How could we represent the weather changes at sea? We could simply think of a wave moving generally from west to east at our latitudes. This wave represents the succession between the areas of low pressure, which we will call L, standing for low, and the areas of high pressure, indicated with a H, says for high, as it is shown on the official weather reports. The depression moves together with the weather fronts. You have then the warm fronts, which we will show in this way, the cold fronts, which are following and indicated in the same way, and close like two scissor blades, getting one on top of the other. In relation to this movement, we need to know where our position is. In general, within the low-pressure areas, the weather is unsettled. On the marginal areas between highs and lows, the wind flows are sustained, whereas dry and fine weather can be found in the middle of the anticyclones. Now let's move on to the wind rotating clockwise around the areas of high pressure. Here's the wind, converging in this way towards the central areas of the depression. This is what happens in the northern hemisphere, but we expect exactly the opposite situation across the seas of the southern hemisphere. There too, the wind always flows from the high to the low pressure areas. The difference, however, is the sense of rotation, which is anti-clockwise inside the highs converging clockwise inside the lows. Once we have explained how the wind rotates inside highs and lows, let's discuss how the buis ballot implies that an observer facing a headwind will always have the high pressure on his left-hand side and low pressure on his right-hand side. As a matter of fact, we refer to a vessel sailing, for instance, aft wind. She is going to have the high pressure areas to starboard and the low pressure ones to port. To understand what the pressure gradient is, let's compare wind with water. And let's imagine we have two containers. One marked H for high and another L for low. If we join the two containers with a tube, the communicating vessels will make it possible for the water to flow and descend from the container placed higher up to the one placed lower down. In the same way, just like the wind, the water always flows from the high to the low pressure. But how does that happen? The higher the pressure gradient is, the faster the flow of water will be. But if we move away the low pressure container, the water will clearly fall more slowly. If instead the low pressure is lowered down, the water, and so the wind, will accelerate their motion. It's understood that by pressure gradient we mean the ratio between the distance of the high and low pressure and their values' difference. The higher the gradient, the stronger the winds. The Coriolis force works on the air masses, deflecting them to the right from their way of motion. We never have to undervalue this effect. It has no particularly practical effect, but it's good to know it exists. Let's see how the wind behaves. We could make a representation of it with a simple example. Let's imagine a snow-covered hill. At its top, a small man on a bobsled, and on the other side, a valley with a downhill slope like a depression, towards which the man will descend. Theoretically, the downhill line is straight, but because of the Coriolis force, the bobsled will go downhill always pulling the lever to the right-hand side, and this is how the downhill run will end up looking. This means that it will get out of the high-pressure region by converging towards the low-pressure areas. The direction of the bobsled will change in this way. In short, this is the path followed by the bobsled, which is the one covered by the winds, roughly speaking. As we said earlier on, the wind aloft is stronger than the wind at ground level. Now, as an example, let's suppose on this side an area of high pressure, and on the other a lower pressure one. The direction of the wind rotating clockwise around the highs and anti-clockwise inside the lows will tend to flow along the isobars. Don't forget also the pressure gradient force, which allows the gradient to push air from the high to the low pressure areas. This is the gradient vector. Assuming this is the wind speed we get, the actual wind will slow down due to friction, and the resulting effect of this vector will induce the wind to deflect towards the areas of low pressure. We cannot get puzzled, as we know that the wind, like the water, flows from a higher level to a lower one. It would be impossible for the wind to have an upward motion to the high pressure areas. This small basic example proves how the wind at ground level is deflected to the left by some 10 or 30 degrees, depending on the terrain roughness. What we are going to do now is a small exercise to clarify how the wind behaves in relation to the isobars. Let's imagine that this is an isobar, but in this area we have two areas of high and low pressure. We want to work out the prevailing direction of the wind in the positions 1, 2, and 3. What is going to be the prevailing wind at the 3 points? The answer is pretty easy, as the wind rotates clockwise and we consider only the area for which data are available in this course. That's how it flows. Now, let's take the low pressure in the same way, as then the wind flows anti-clockwise. The wind in this area will follow this path. But friction will deflect the wind to the left of isobars. The resulting direction will be 1, a southerly wind. 2, a southwesterly wind. And 3, a southerly wind. This means that every time we examine a synoptic chart, it's first necessary, in relation to the isobar, and therefore our position, to understand where the areas of highest pressure are located and where the lowest pressures are, in order to be able to work out the prevailing direction of the wind. Let's now have a look at the clouds, focusing on the so-called orographic clouds. Let's imagine a mountain on one side, and on the other the sea facing it. When the wind arrives along this direction, it will be forced to rise. The air then, as it rises, will tend to cool down, and at some point, known as the condensation level, clouds will form. This is the so-called Stow effect, with precipitation upwind. When the wind is strong, it will tend to continue its way up, climbing over the mountains. Before falling downhill, it will get compressed downwind. It will have an effect on temperature that will rise, thus fading the clouds away. As an onset of a wave pattern, the wind lifting to a certain height will lead to the formation of those typical cuttlefish bone-shaped clouds, the so-called altocumulus lenticularis. When a boat sailing along the coast spots this type of white cloud, isolated and stationary in the sky, one can suppose that the very strong prevailing wind is blowing next to the area of the mountains close to the coast. This could be a warning to the skipper or the captain to navigate closer to the coast to avoid an excessive increase of the sea. We've already gone through the coastal breezes. Let's imagine being in a bay with a good anchorage, somewhere to spend the night. The boat arrives in the afternoon, when the sea breeze picks up around, say, 15 knots from the southwest. The boat bow will align with the headwind, the anchor will be dropped, the chain let go. That's how the orientation of the boat will be. During the night, after sunset, the land cools down more rapidly, whereas the sea stores some spare heat. In this case, the breezes will tend to come from the mainland, and the orientation of the anchored boat will change. If, however, towards midnight, for example, the breeze direction carries on coming from offshore, it's clear that there's not going to be any more a regular succession of the sea-land breezes along the coast. This will make the captain think as to whether this is the wind being observed. It's likely a new weather disturbance is on its way, as we are dealing with a gradient wind. Wind names can sometimes be taken for granted, but it's good to refresh our memory. From the north, there comes the tramontana. From the northeast, the grecale. From the east,
il Levante.
where the sun rises. From the southeast, the sirocco. From the south, the ostro, or southerly wind. From the southwest, the libiccio. From the west, the ponente, where the sun sets. From the northwest, the mistral. The important element to remember is that the wind blows always from a certain point in a certain direction, just as if the observer's position were at the centre of the compass card. An important element to keep in mind is the prevailing direction of the wind in relation to the coastline. This is useful to fully understand what fetch means. If the wind blows from the mainland, even at a high speed, say 30 knots from the northeast, the boat sailing next to this coastal area will never encounter a rough sea, as the distance between the coast and the boat herself does not allow her to observe the sea when increasing. On the contrary, if this boat would navigate next to the coast with the wind from the libeccio, southwest, as this coast is exposed to this wind, there you get a much rougher sea, and the boat would better move away from the coast for greater safety. When you listen to a weather report, for example the Meteorology bulletin for the Italian seas, and instead of writing down the full text of the report, which could be complicated and boring, you can try to represent the weather using the universally recognized meteorological symbols. They're quite simple and intuitive. For example, the warm front is marked in this way. The rounded line of the front indicates its direction of movement. This is a mass of warm air about to break in. This is how we indicate the cold front and the cold air breaking in. The troughs bringing thunderstorms are shown simply with a line.
si indicano semplicemente con una linea.
If you see on the charts thick lines like this is the direction of the movement of the line, and down there is where the thunderstorms can be expected. The areas of high pressure are indicated with an H, which stands for high pressure. The lows with an L, which stands for low pressure. The X's on the synoptic charts show the lowest value of the depression. The cloud coverage can be represented on the various sectors by a small circle subdivided into 8 sections of the overcast percentage. If half of this circle is blackened, you get 4/8 of the overcast sky, which will appear as partly cloudy. When instead the sky is completely overcast, the whole of the circle will be black, and, in this case, there are 8/8 of overcast sky. This, then, is the way the wind is indicated, using a long arrow showing the direction, in this case, northeast, whereas the wind intensity is shown by wind barbs. 1 barb only for a 10-knot speed, 2 barbs for 20 knots, half a barb for 25 knots. When the wind reaches 50 knots, then the wind barbs will be replaced by a small black triangle. In this case, the wind blows from the west at 50 knots. In the presence of thunderstorms over the sea, this symbol can represent the situation in this way. This is the symbol of thunderstorms developing in the area. If we observe thunderstorms approaching and we calculate the time interval between the lightning strike and the rumble of thunder, we can as well approximately calculate when the storm is approaching. As the speed of light and therefore of the lightning is instantaneous, and as the speed of sound is 330 meters per second, a time of 10 seconds between the lightning and the thunder means that the storm is going to be about 2 miles away. In fact, 330 meters by 10 seconds equals to 3,300 meters, and therefore the distance can be calculated in about 1.5 or 2 miles.